Good day, everyone. This lecture will introduce the core problems that we will be considering in this course, namely the estimation problem and the hypothesis testing problem. The second one is also referred to as the classification problem in context of machine learning or artificial intelligence, and as the detection problem more in context of electrical engineering. For motivation, we will start by looking at a problem that arises in an engineering application, yet the mathematical formulations that we will be adopting throughout can be applied in virtually any discipline that involves inference. Suppose that we wish to determine the distance between a sensor and an object. To this end, the sensor sends a pulse and receives its reflection on the target. This can be illustrated here. In this figure depicts the light intensity at a point in the vicinity of the sensor. This is the transmit pulse, and the receive pulse is a delayed, scaled, and dispersed version of the transmit pulse due to propagation phenomena. Our sensor obtains measurements of this delay between these pulses, and this operation is repeated over and over. So n pulses are sent, and therefore we obtain n measurements of this delay, right? So to estimate, if our goal is to determine the distance from the delay, we obviously need a model that relates both quantities. And in this case, we can't just use the fact that the distance traversed by the pulse divided by the delay should equal the speed of light, right, which is a known quantity. Or equivalently, the distance equals c halves times this delay, right? The measurements provided by the sensor will be denoted in this way, and it can be expressed as the true value of the delay plus some measurement error or perturbation, typically called noise in this context. So the problem is given the speed of light and given the data, the measurements, we need to estimate or to guess the value of this distance. And notice the notation for vectors with an underscore to denote column vectors throughout. So we will be addressing this problem from a rigorous point of view throughout the first half of the course, but for illustration purposes, in this slide, let's apply our common sense to come up with our best guess of how we could solve this problem. So perhaps the most natural approach that a human being could come up with in first place is just to use the fact that use this relation over here and use the fact that the measurements sort of provides us with the delay to just plug any of these measurements in this expression, right? So for instance, we can just use the first delay measurement in this expression over here to obtain an estimate, right? And this is indeed a very nice first attempt, but we can see that this just amounts to ignoring the effect of this noise. However, given the fact that we are we have n measurements available, just throwing away all but one doesn't seem like the smartest approach we can follow. So the next most natural thing we can think of is to average these measurements with, and we would expect that the resulting average will provide closest value for the mm, true delay than each of these measurements individually, right? So the effects of the noise in that case is said to be averaged out, and the more measurements we have, we expect that the resulting average would be closer to the actual value of tau, right? So after plugging the average in this expression over here, we would come up with this estimate, which will be denoted in this way with x bar to denote the average or sample mean of the data. And please note that the average or sample mean is a totally different concept from the expectation or mean of a random variable. This is a deterministic quantity associated with a distribution, whereas this is a function of the data, right? And since data are typically modeled as random variables, the average or sample mean is also will also be a random variable. This was an example of an estimation problem, but estimation problems arise in many applications. Radar is a very related example where the received pulse can be used not only to determine the distance to an aircraft, but also its speed and perhaps its model. In sonar works under similar principles. In this example, this ship is capable of estimating the angle of arrival of a reflected acoustic pulse by looking at the different times at which the pulse is received at multiple sensors. A different application is speech recognition, where one needs to determine the sequence of words pronounced by a speaker. Or in wireless communications, where a transmitter modulates an electromagnetic wave to transmit a sequence of bits. The receiver then needs to reconstruct the transmitted sequence by looking at the received signal. In localization, a GPS sensor may look at the relative distances to a set of satellites to estimate its position. And many other estimation problems arise in medicine, biology, psychology, finance, and in general in any application or any discipline that involves learning from data. The first thing we need to do to specify an inference problem is to provide a model, which is essentially a mathematical abstraction of some phenomenon in reality. It comprises mathematical objects such as scalars, vectors, functions, random variables, matrices, sets, and so on, and their relations among them typically expressed by means of equations, inequalities, or distributions. I like to think that if the model was a movie, these objects would be like the actors, and the constraints would be like the screenplay linking the role together. If you haven't done so, I recommend watching a video earlier in this series that provides a review on probability theory, and specifically it reviews the concept of model and probabilistic model, which will be used throughout this course. After specifying the model, we need to indicate what information is known. In our example, it was the speed of light and the measurements, also known as observations, samples, and so on, even data instances, data vectors, etc. The rest of information is unknown, such as the noise and the distance in our example. Out of this information, we are interested in knowing part of it. In this case, we are requested to estimate the distance. The rest of information is neither known nor we are interested in knowing it. It's just there to disturb us. It just makes the problem more complicated. So this course will develop a systematic approach to solve, or at least to address, estimation problems. But before embarking in such a quest, let us revisit our previous example on range estimation to gain some intuition. So the estimates that we considered so far are totally fine if the object is allowed to be at any distance from the sensor. But suppose now that the object of interest is a car, and the car needs to move on a road. And suppose that we know the distance from the sensor to each of the sides of the road. In that case, the true distance should be some number between A and B. Note that I am neglecting the width of the car for simplicity. However, our scaled sample mean it may fall out of this interval because of the effect of noise, right? And in such a situation, it makes little sense to return an estimate that is less than A or greater than B, right? So in this situation, what intuition tells us to do is that if our scaled sample mean is less than A, we can just return A. If it is greater than B, we can just return B. And if it is in the interval AB, we just return the scaled sample mean as is, right? Another example would be this one, where the object of interest is a cart or a train and needs to move on a pair of rails. And suppose that we know the distance between the sensor and each pair of rails. So it is very unlikely that the scaled sample mean is exactly one of these distance over here. So what intuition would tell us to do in this situation is to return the value out of these three that is closest to the scaled average. So so far these estimates that we have proposed are derived based on intuition, right? But of course, intuition doesn't always work, especially in more complicated situations. So to develop a more general and systematic approach, let us look at this same problem from an alternative perspective. So to this end, let us assume that the noise is Gaussian distributed with mean 0 and variance sigma squared. Under this assumption, it is straightforward to see that the delay measurements are Gaussian distributed with mean the true delay and variance the same as the noise. And one can use this assumption to compute the distribution of the scaled average in these three situations over here. So for instance, the orange curve denotes the distribution of the scaled mean when the cart is on the first pair of rails. So whenever we receive our data from a sensor and we compute the scaled average, then we will obtain some value along this axis, right? And one can look at that, one can note that for each value of this scale sample mean, not the three possibilities are equally likely, right? So for instance, if we obtain a value close to 10, it's very likely that it has been generated by this first case when the cart is on the first pair of rails, and so on. So this estimation problem can be alternatively seen as as choosing what is the distribution that most likely generated what we are observing. Note as well that the width of this bell is proportional to the standard deviation of the noise. So if the noise has a very small standard deviation, so we have a low measurement error, then this distribution would be highly concentrated around 10, this one would be highly concentrated around 30, and so on. So there, this means that for each value of this scale sample mean, it will be very clear what is the most likely distribution that produced it. On the other hand, if the noise has a very large variance, right? So we have a large measurement noise, then these distributions will be pretty flat, and for each value of this scaled average, it wouldn't be as clear what is the one that generated it, right? So they would overlap quite a lot. So now let's generalize this interpretation to an arbitrary estimation problem. So to this end, we will be thinking of probabilistic models as families or sets of candidate distributions, right? So for example, in this range estimation example, the measurements are Gaussian distributed with where the mean can take one out of these three values. So in this case, the family of candidate data distributions contains three elements. But this perspective can be applied in general to virtually any probabilistic model. So to reflect that, we will be using this set notation, where here this parameter or vector of parameters identifies each distribution. So here the parameters are sort of the ID of each member of the family. And capital theta will be used to denote the set of all possible values that those parameters can take. At this point, we have to be especially careful with notation Calligraphic P will be used to denote this family of data distributions, whereas capital P will be used to denote the distribution, essentially the probability measure for this value of the parameters. If that doesn't sound familiar to you, you may want to watch the review video on probability theory if you haven't done so. Also note that I used here theta prime rather than theta to stress that this is not the value of the parameters, the true value of the parameters. This is just an auxiliary variable or dummy variable, local variable used to define this set over here. So for one example, in our example, this P, capital P, is the distribution where each measurement is Gaussian distributed with these parameters, and the measurements are independent of each other. Note that if I don't say the second part, that the measurements are independent, I am not specifying completely this distribution, right? Because I would just be providing the marginal, right? As an exercise, you may want to stop the video and write the marginal PDF of each measurement and the joint PDF of all measurements together. We will provide the solution in the next slide. So with this perspective, summing up, an estimation problem is to determine which of the distributions in this family generated the data that we are given, or equivalently to find the ID of the distribution that generated the data. This is the solution to the exercise in the previous slide. This expression provides the PDF of a Gaussian distribution with the parameters mu and sigma square. Therefore, the marginal PDF of the measurements can be obtained just by substituting here the value of its parameters. And due to independence, the joint PDF can be obtained by multiplying the marginal PDFs. It's important to remember that the product of the exponentials equals the exponential of the summation. Also, note here that lowercase p is used to represent PDFs. In this case, this will be the PDF associated with distribution capital P sub theta. So to build further intuition and to digest this general perspective on estimation problems, let us look at another example that is fundamentally different from the one that we looked about range estimation. So suppose that we would like to determine the fraction of blunt Norwegians. Let to this end M, capital M, denote the total number of Norwegians, and little m denote the number of blunt Norwegians. And now suppose that we can start making calls where we select one Norwegian uniformly at random. We ask the color of their hair and set xn to be 1 if they say that they are blonde, and 0 otherwise. Therefore, the probability that xn equals 1 is the number of blonde Norwegians divided by the total number of Norwegians, so the fraction that we want to estimate. And another way of saying this same thing is that xn is Bernoulli distributed with a parameter theta. And also, if we choose each person that we call independently, then xn and xn prime will be independent for n different from n prime. As an exercise, you may want to write the marginal of xn and the joint PDF of x, and that will give us the distribution capital P sub theta. Therefore, the family, our model or family of distributions can be expressed in this way, where the parameter can take a value within this interval. This will be therefore our capital theta. And by the way, I will be omitting the prime whenever it is clear from the context. So the problem is, given the vector with all these observations, estimate theta, right? And perhaps the most reasonable estimate that any human being would come up with is the number of blunt persons that we called divided by the number of persons that we called, right? So this is this summation divided by n, which is essentially the sample mean of the x. Again, this is based on intuition, and we will be developing the more solid foundations in subsequent lectures. Yet another example. Suppose that we would like to estimate the width of a hole in the roof, and to this end we observe where raindrops fall on the floor. Let xn denote the distance from the position where the nth drop has fallen to the origin, which is placed right under the left endpoint of the hole. So in this situation, it is reasonable to assume that xn is uniformly distributed between 0 and theta, and that these positions are independent of each other, precisely because of the physical process that generated the drops. Again, you may write the marginal PDF and the joint PDF. The model will be given by this set, where our capital theta contains all possible values of theta, which in this case are all positive numbers. This is the notation that will be used, R plus, to denote the set of non-negative real numbers, and R plus plus for the set of strictly positive real numbers. Okay. The problem is therefore, given the position of where all drops have fallen, to estimate this width here. And perhaps what our intuition asks us to do is to return the maximum of these positions as an estimate. That's it. We will just look at the drop that has fallen to the most to the right to determine the distance. The rest of drops will be essentially ignored. Okay, so far we have looked at very different application examples. However, it is impossible that a course covers all possible applications where an estimation problem arises, right? So because of that, we will be assuming from now on that the model is given, because the model is the application specific part, and therefore it will be the responsibility of the practitioner or the researcher that wants to apply this theory to develop a model for her or his own application. So let's look at a few more examples, but this time we will not be providing a possible application where these models may come up. One example can be, for instance, the xn is Gaussian distributed with mean 0 and variance sigma square and independent of the other xn's. In this case, the model needs to specify that sigma square needs to be positive because it is a variance, right? If xn is Poisson distributed, we have a similar situation where the parameter also needs to be positive. In so far we had only one parameter, but it's also possible that we have more than one parameter, as in this case over here. Instead of having a scalar theta, here we need a vector theta that contains these the two parameters, and the set capital theta will contain all tuples of real numbers where the second one is of course positive. A similar example will be this one where the random variables are uniformly distributed. In this case we also have two parameters, but the restriction is that the second one has to be strictly greater than the first one. And so far we always assume that the observations are independent of each other, but this need not be the case. For example, here we only have two observations, but they are correlated as captured by this correlation coefficient rho. So here we have three parameters, and the constraint is that the third entry must be between -1 and 1. So again, I recommend writing the marginal and joint PDFs, especially for this last case, which is the most interesting one. So now just a few remarks about notation so we don't get confused. Xn is the nth observation, but depending on the context, it can represent a random variable, right? So for instance, when we write something like this, it is clear that this thing is random. However, it can also denote a real number, so a deterministic creature, right? It can be the value, for instance, that we have observed, right? Or like this here, it's the value where we evaluate a PDF, right? So of course we could use different notation for to distinguish between these two different things, right? Because they are like different objects with the same name, right? But since the context reveals what we are talking about at each time, then we don't make our notation unnecessarily complex. This is a common practice in statistics, by the way. X underscore will denotes the vector column vector with all the observations or measurements, whereas x bar is the sample mean. Okay. Calligraphic P, as we said, is the set of distributions in a model, and capital P is a probability distribution or probability measure. Okay. Lowercase p it will be used to denote PDF, and depending on what we put inside, we will this will be a marginal PDF or a joint PDF, right? So these two functions are again different things with the same name, right? So it is important to keep this in mind, not to get confused. And theta will be used to denote either the true value of the parameters, the one that generated the data, or a dummy or local variable, as we did before. So now we get to one of the most important concepts in estimation theory, and this is the concept of estimator. The motivation is that we cannot start to think what is the estimate we want to provide every time we receive a new observation, right? We need an algorithm or a rule that allows us to compute the estimate from any possible value of the observations, right? In this way, we can code this algorithm in a computer or in a microcontroller or something like that. So the approach is that we do all the thinking when we design the algorithm, and then we just run it time after time every time we get a new x. So let calligraphic x denote the set of all possible values that the observation vector can take, and let capital theta, as before, be the set of all possible values of the parameter vector. An estimator is defined as a function that takes a possible value of the observations and returns a possible value of the parameter vector, right? And there is the restriction that f cannot depend on unknown quantities. So, for instance, on the noise or on the parameter that we want to estimate. Let us be clear about the terminology. An estimate is a number or a vector, right? What we obtain by evaluating this function here, and f is the function itself. Okay, it's very important not to confuse these two words. There's also the word estimation, which is precisely what we are doing. This is the activity we carry out in this course. We do estimation. And also the verb to estimate, which means to compute an estimate. Okay, so it's very important not to make mistakes with this. As a note that the definition here doesn't require that this function gives a good estimate, right? So it just it must give just some valid value inside this set over here. So we will see down the road what we will call a good estimator or a bad estimator, but even a stupid estimate, an estimator that returns a stupid estimate qualifies as an estimator, right? In the example of the first slide, the data space is clearly the set of all n tuples of non-negative real numbers, because they are measurements of delay. And the parameter space is essentially the set of non-negative reals, because they are distant, and this is a distance, right? Possible estimators are, for instance, these two, which are just the estimates that we saw in the first slide put in function form, but one can also conceive many other possibilities, like, for instance, this estimator over here, or this one over here, So you see that they return a positive real number, so therefore they are estimators, fully qualified estimators. Different question is whether they are good estimators or not. Something that wouldn't qualify as an estimator is this function over here, and the reason is that it depends on something that it is unknown. So far we have focused on the estimation problem, and this is what will keep us busy in the first part of the course. The second part will deal with the hypothesis testing problem, also known, depending on the context, as a classification or detection problem. And this is what we are going to briefly introduce right now. The hypothesis testing problem is intimately related to the estimation problem. In fact, the modeling part is the same. What changes is that we are no longer required to provide the exact value of the parameters. Instead, we are given two sets, theta 0 and theta 1, that split the parameter space into two disjoint parts, and we are just required to say in which of them the parameters are. So in this example, we are not interested in the distance, the precise distance between the sensor and the cars, but it is enough to knowing in which lane the car is. So, for example, the set theta 0 may comprise all the distances that are less than or equal to this distance here, and theta 1 may contain the others. We have to decide between hypothesis H0 that states that theta is in theta 0, right? And hypothesis H1 that says the opposite. The hypothesis H0 is typically known as the null hypothesis, and hypothesis H1 is typically known as the alternative hypothesis. And as I said, this problem may receive other names. For instance, in the machine learning or computer science environments, one can talk about or prefers to talk about classification. Whereas in electrical engineering, such as radar or communications, one prefers the term detection. So in the same way as we used estimators to solve estimation problems, we use tests, also known as classifiers or detectors, to solve hypothesis testing problems. And their definition parallels that of an estimator, with the exception that the function should not return a possible value of the parameters, but one of the hypotheses under consideration. So again, it is important to note that any function assigning one of the hypotheses to each possible value of the observations qualifies as a test. Another question that we will address in the second part of the course is whether a given test is good or not. In our lane detection example, one can think of what is the a possible detector, and perhaps the most straightforward alternative that one can think of is to decide that the car is on the left-hand lane if our scaled average is less than or equal to d, and decide that it is on the right-hand lane otherwise. But again, this is just intuition, and this is not a systematic way of coming up with a test. This is just a toy example But hypothesis testing problems emerge in a myriad of applications. For example, one before a vaccine or a drug is approved, it has to be tested on a sample of people, and then, depending on what is observed, one needs to decide whether the vaccine or drug it is effective or not, for example. And this has to be done systematically because there are lives involved and also large amounts of money, right? In the context of social sciences, a toy example would be to determine whether the wage is correlated with gender, right? So, two hypotheses: it's correlated or not correlated. In the context of radar, one may want to detect whether there is an enemy aircraft or not, right? In a car, there are sensors mounted in the front that detect whether a collision has occurred or not, perhaps to trigger the airbag, right? And there are, of course, also obvious surveillance applications like detecting whether there is an intruder in a certain area or not, right? So in this case, we are all talking all the time about two hypotheses, but of course, this can be generalized to multiple hypotheses. So, in view of this discussion on estimation and hypothesis testing problems, there are several open questions that we need to answer. For example, how to design an estimator or what constitutes a good estimator. These are questions that we have addressed so far from a purely intuitive point of view, but we need to develop a systematic approach. It's also useful to know when a given estimation problem is difficult because that can offer indications on whether we need to collect more data or whether we need to buy a better sensor with lower measurement noise variance, for example. It's also interesting to know how well we can do in a given estimation problem. So if we have, for instance, a bound on how well we can do, and we have an estimator that already is close to the bound, then there's no use spending more time trying to come up with a better estimator, right? And similar questions arise also for detection. I would like to emphasize that although the toy examples that we have chosen today are pretty intuitive and arguably simple, in reality, problems are typically more complicated, and there's no possibility to develop an estimator or a test just based on intuition. So that's it. We have a pretty interesting agenda for the rest of the course, as you can see. Thanks for watching, and I'll see you in the next lecture.